Assalamualaikum and hi everyone. This lecture is about decomposition techniques. However, this video will cover only on recursive decomposition and data decomposition. So, actually there are four types. Another two is called as exploratory decomposition and speculative decomposition. In this case, decomposition is the technique on dividing the problem into sub-problems, or in this lecture we discuss about the one big task will be divided into several sub-tasks. Okay, so let's look at the first decomposition, which is called recursive decomposition. So recursive decomposition is using divide and conquer strategy, where a given problem is decomposed into a set of sub-problems. These sub-problems are recursively decomposed into several subtasks until a desired granularity is reached, which means until the target or the end of the task is met. Okay, so let's look at the example. In this case, we are going to use recursive decomposition in sorting a list of number by using quick sort. As you can see there are a list of numbers being given, and then the numbers will be sorted into ascending order, which means from the smallest to the largest. Okay, so to sort this number by using recursive decomposition, so you need to find a pivot value. So in this example, the pivot value is chosen from the first number of the list, which is 5. So to divide into the subtasks, first we need to consider the number which is less than pivot value, and then will be divided to the left, and the number which is equal and largest to the pivot value will be divided into the right side. Okay, and then as you can see there, the number which is less than 5 will be listed at the left, which are 1, 3, 4 and 2. Okay, taken from here. Okay, do not sort the number yet, you just tick and put it as is in the list, okay, at the left side. Okay, and then at the right side we take the numbers which is equal and largest to the 5, which is 5, 12, 11 until the rest. Okay, and then we put into the list. Okay, then the next part is you need to identify or select the next pivot value in level number 2. So in this case, is in the list of 1, 3, 4, 2, it choose 3 as the pivot value. So the number to the next level, which is less than 3, is equals to 1 and 2. And the number which is equals and large or more than 3 is 3 and 4. Then there is no other numbers need to be sorted. So we just sort the number to the end. Okay, so it will become 1 and 2. So same goes with this one, which is 3, and then the right one is 4. So we do the same process at the right side. Okay, so from the list, find the pivot value. So in this case, it choose 9 as pivot. So whatsoever number which is less than 9 will be put at the left side, and the number which is equal and more than 9 is put at the right side. So do the same processes, okay, on each level until the end of the process. So then we get the sorted number from ascending or from the smallest to the largest number. So this is the end. Okay. So when you do this kind of decomposition, so your workflow, do not forget to highlight the pivot value so that we can notify, oh, this is the pivot value that you have chosen in each level. Okay. So in this example, once the list has been partitioned around the pivot, each sublist can be processed concurrently. So let's say at the level 2, there are 2 concurrent processes can be run concurrently. And at the level 3, there are 4 processes that can be run concurrently, and so on until the end of the numbers that being sorted. Okay. This process is being executed repeatedly. Okay, repeated recursively. Okay, so this is the algorithm, the fundamental of recursive algorithm, which is a simple serial loop for computing the minimum entry to find the minimum value on each list numbers. Okay, this algorithm actually can be enhanced in order for us to find the recursive to do the recursive decomposition. So let's look at the next one. Okay, this is the enhanced algorithm. Okay, to apply the recursive decomposition where we need to find the left minimum and right minimum. Okay, basically taken from the previous algorithm. Okay, so this is another example. In this case, to find the minimum value from the list. So let's say given to us is the list of 4, 9, 1, 7, 8, 11, 2 and 12. So we want to find the minimum value within these numbers. So it started with from the bottom level. Okay, it compared two numbers between the set 4, 9, 1, 7, 8, 11 and 2, 12. So from this set, so we need to find the minimum value in this case, which is 4. And then between 1 and 7 is 1. Between 8, 11 is 8. And between 2, 12 is 2. And then do the next process. Okay. For the next level until the desired output is reached. Okay. So however, you can also do this from the top to level. You list the list of numbers, okay, first, and then you find the minimum value, and then the arrow is to the bottom level. Okay, next one, finish our recursive decomposition. So we proceed on data decomposition. So identify the data on which computation are performed. So if we use data decomposition, we need to consider the data that we use. Okay. And then we will do the partition. Okay. This partitioning induces a decomposition of the problems. Data can be partitioned in various ways. This critically impacts performance of a parallel algorithm. So data can be partitioned in many ways. Okay, so we will look the several ways or method on how we want to decompose the data. So the first one is by looking at the output data. Okay, so often each element of the output can be computed independently of others. So we are looking at the output data, and then usually the output data is independent from one another. So then it can be decomposed. A partition of the output across tasks decomposes the problem naturally. So when we decompose the data based on output, so basically it will guide us on the decomposition process to the next level naturally. Okay, so the input data also will follow the output data that we have decomposed or divided. Alright, so this is example on multiplying 2 by 2 matrices A and B, n by n matrices, which is we have matrix A and B here, and then we get the output of C. So if you want to do the output data decomposition, we need to look at the output, which is C. So C here consists of four answers of 4 elements. So we need to divide the task into 4 subtasks. Okay, so as you can see there, task 1, task 2, task 3 and task 4, okay, is obtained from the decomposition of the output here. So C11 is is obtained from the process A11 multiplied with B11 plus A12 multiplied with B21. So say similar to the rest of tasks. Okay. Okay, so another example, we have another option here, two options, decomposition 1 and decomposition 2. Basically, not only 4 tasks that we can use to decompose the matrix. However, if we have other algorithm, so that algorithm can be enhanced or can be differentiated. Okay, actually it depends on how we write the algorithm. So in this case, the task 1, okay, to obtain the C11 is from A11 multiplied with B11. So if you can see there, the difference between decomposition 1 and decomposition 2 is at the task number 3, number 4 and number 5, whereby these 3 tasks switching their element in getting the output of C. Okay, so task 3 C12 is obtained from A11 multiplied B12. However, in this decomposition 2, task 3 is getting from the multiplication of A12 with B22. Okay, same goes to the rest of tasks. Okay, so this is another example. Consider the problems of counting the instances of given item sets in a database of transaction. So in this case, the output, okay, this is the output, the item set frequencies can be partitioned across the task. So we need to divide the item set frequency into several subtasks. So the diagram shows you that the item set frequency is divided into 2. Okay, so task 1, okay, is holding the item set frequency from 130 and 2. Meanwhile, task 2 hold the frequency from 1200. So the database transaction and item set still hold the same value. However, the output, the only item that have been changed or divided into several subtasks. Okay, so this is another example. All right, so from the previous example, okay, that we have discussed in the previous slide, if the database of transaction is replicated, means we copy and paste, okay, we copy exactly the whole database transaction across the processes. Each task can be independently accomplished with no communication. So there is no communication is needed when we do or execute task 1 and task 2 because the database transaction has a complete data set to be referred. However, if the database of transaction is partitioned, if we divide into several division or several part across processes, okay, in terms of to consider our memory storage, okay, each task first computes partial counts. So we cannot proceed or fulfill the whole task, okay, 100%. So that one we only can proceed only several or partial parts, and we can only count the item set frequency on several parts only. So these counts actually, so how to complete the count, we need to aggregate or integrate all the tasks that we have partitioned in earlier stage at the last stage before we accomplish or complete the task, the whole task. Okay. Alright. So that one is output data partitioning, and next one, another types of data decomposition is called input data partitioning. So we want to, or we decompose the data by looking at the input data. Okay. So why we need to look at the input? Why input data sometimes is needed to be decomposed? Because we do not know the output clearly. Okay. In early stage, we don't know the output of the data, so we can't decompose based on the output data. So in this case, we need to use the input data to partition our tasks. Okay, so let's look at the example. We're still using the same example. Okay, so if you can see here, in output data decomposition, we did not divide the database transaction into several parts, but in input data partitioning, we divide the database transaction into two parts. This is one part, this is another part. But however, we do not touch the item set and also item set frequency. So when we want to find the item set frequency, we can only find in the set of 1, 2, 3, 4, 5 database transaction only. So the output data actually is not complete yet. So we need to wait for the task 2 to be finished in order for us to finalize the item set frequency between task 1 and task 2 to get the complete item set frequency for the whole problems. Okay. Okay, so this is example. Another example. This case, the partition is involving the input and output data. So we can divide the input and output data in one process. Okay. So as you can see here, we divide the input data and also the item set with the item set frequency. Okay, and then divided it into 4 subtasks, task 1, task 2, task 3, and task 4. So in this case, the output is not complete yet, so we need to aggregate all these 4 tasks of item set frequency in order for us to get the complete set of item set frequency for the last output. Alright, so we have another types of partitioning. It is called as intermediate data partitioning, whereby we can use one of the intermediate stages instead of input and output. So we also can use intermediate stages as the basis for decomposition. So this is an example of intermediate data partitioning. Okay, the example of dense metric multiplication. So in this case, it just take a part of the multiplication process between A11, A21, and B11 and B12 and get the output here. And then the next process subtask between A12, A22, and B21 and B22, and then we get the output here. Okay, so to get the complete set, you need to combine or aggregate between the output from task 1 and the output from task 2 to get the complete result. Okay, C11, C12, C21, and C22. Okay, so next. So another example. Yeah, this is the complete example of the previous slide. So we have this kind of matrix A and matrix B. So if we multiply A and B, we will get 8 output of D. Okay, so this 8 output of D or 8 tasks. Okay, we need to have 8 tasks to get the 8 output. So this is the first stage. So the second stage to get D1 until D2, we can divide these 8 tasks into 2 subtasks. Okay, like this, like shown in stage 2. So the first task and the second task, when we total out, we will get another 4 tasks, which is C11 and C12, C21 and C22. So this is the final result of multiplication matrix A and B. So and the last one actually is the combination of 8 tasks with 4 tasks. And finally, we will have 12 tasks to complete or to get the final matrix result. Okay, so as you can see here, we not only the task actually is not fixed into either 8 or 4. It's depend on how we write the algorithm, okay, on how we partition the data and what kind of partitioning type that we use to decompose the tasks into subtasks. Okay, so this is the task dependency graph. Okay, is generated from the previous example. So here we have 12 node of tasks, which is taken from the 12 tasks that has been created to get the result of C just now. Okay, and the rest still the same. So node 1, 2, 3, 4 until 8 is represent the D. Right. Okay, so the last one is the owner computes rule. So owner compute rules generally states that the process assigned a particular data item is responsible for all computation associated with it. Okay, in the case of input data composition, so the owner compute rules implies that all computation that use the input data are performed by the process. If you use input data decomposition, and the owner compute rules implies that all computation that use the input data are performed by the process. So all the input must be performed by the process. If we use output data decomposition, so the owner compute rule said that implies that the output is computed by the process to which the output data is assigned. Okay. Okay, so to conclude what we have learned in this lecture, so we have learned 2 types of data decomposition, which are recursive decomposition and also data decomposition. So recursive, the process will be repeated accordingly until the result is reached, and the data decomposition actually is depend on what kind of data that you use to decompose, either input data decomposition or output or intermediate data decomposition. Okay, thank you.